lot of people in the audience, and
There we go.
a lot of people here, and what side does that go off? There we go. Okay. Oops. Okay. Anyway, so yeah, we'll just kind of get jumped in here so a little bit. So who knows about the James Webb Space Telescope? We'll start there. Okay, good. Who has looked at or seen some of the images from the James Webb Space Telescope? Excellent. Okay. Who woke up on Christmas Day 2 years ago to watch the launch of the James Webb Space Telescope? Yes. Okay. That's so good. People shut up. Great. Anyway, so you know, from the initial image and data dump that we got, and from every single image and data that we have received since then, we've really received some of the clearest, sharpest data that we have ever gotten from astronomical sources. Full stop. Like it's really quite incredible. So what I wanted to talk about tonight is not so much about, you know, like the objects or like the history of the James Webb and like the launch and everything like that, but really what are we looking at in these images, this visual representation of data from all these spectacular results from the James Webb, kind of from a viewpoint from an astrophotographer. So I've been an astrophotographer now for about 9 years or so. And of course, as soon as I heard about it, started kind of keeping my eye on it about like, at this point, 17 years ago, when like, they first started building this, planning it out and things like that to launch with all the delays and things like that. And so basically, I wasn't even into astrophotography when the James Webb Space Telescope program started. But I've kind of developed my interest and expertise since then. And one thing is that like astrophotographers are technology nuts. We want to know how it all works. We are perfectionists about our gear. We want to know how the lenses interact with every single piece of gear. And it seemed that like in all of the James Webb information or presentations or putting forth about all of the data captured, that was missing. So I decided to kind of fill that gap tonight. So with all the James Webb stuff and all the information that's out there, all of the very well-deserved hype and amazingness from this telescope, what can we learn and know about this fantastic piece of gear as if we approach this not from some super high-tech foreign NASA-only thing, but let's approach this from an amateur astrophotographer's viewpoint and get some analysis and get some viewpoints about what this data actually is and what the telescope is from just an amateur nut. So tonight, I'm covering these kind of 4 general topics here: the optical design, calibration, collimation, and artifacts, which is something that us astrophotographers chase down forever. That's actually part of the enjoyment of the hobby. A field of view in terms of what are we actually looking at in the sky with the James Webb, and probably what I get most asked the most commonly from anybody about my own images, about astrophotography in general, for anything that isn't just like the moon or the sun where we kind of already know about it, but from data to images. Are those the real colors? Is that what the objects really look like? We'll talk about that. So first of all, do you want to talk about the optical design? So a couple of statistics that you might already be familiar with, but the primary mirror or the primary mirror array is 6.5 meters or 21 feet in diameter. So the light gathering area of 25.4 meters or 273 square feet. So nice classic image here that for anybody familiar with the Hubble, that is the primary mirror of the Hubble. That is a general human. I think they have that scaled to 6 feet. And so the Hubble primary mirror sits in the back right there. In comparison, the James Webb Space Telescope primary mirror array is that large and sits on a sun shield, human for scale, right about there. So in astrophotography, we talk commonly about like the light gathering power. It's not always, you know, how faint of a thing can a telescope capture? Well, it's entirely determined by the size of the telescope. And so it follows the area. And so if you double the diameter of the telescope, then you are quadrupling the light gathering power of the telescope. So by area, comparing the Hubble to the James Webb, this is a monstrous improvement in many, many ways. So the design of this, if you're familiar with like reflectors or refractors or Schmidt-Cassegrains or things like that, this is formally a Korsch style 3-mirror anastigmat design. What does that mean? Ultimately, it's just a series of mirrors. But every single mirror in the optical pathway from that primary array, the secondary mirror, the tertiary mirror, and then the quaternary mirror, which we're not really going to talk about too much. But all of those then, because the light is bouncing off of all of those mirrors in a particular way, well, every single type of lens design or every single type of optical design in astronomy has some sort of optical aberration or some sort of imperfection in being able to pass that light through the telescope. This design allows the curvature of each of those to just be slightly different, slightly altered, and in unison with one another to correct for all of those aberrations. So it's pretty much aberration-free. This is ultimately one of the most pristine optical devices that humankind has ever created. It is as close to optical mathematical perfection as we've ever built. But at its core, it uses just a series of mirrors. This makes it a reflecting style telescope. So, in general, we have our, right here would actually be a cutaway, a side view of the primary mirror. We have the secondary mirror out here. So incoming light hits the primary array, goes out to the secondary mirror, back to a tertiary mirror, and then ultimately down to the sensor where it captures that light, captures that data. You can see that better here. So we've got the 18 primary segments. We just have a light cone here, but light comes in, hits the mirrors here, bounces back to the secondary mirror, goes into this cone here, and then hits a third mirror that drives it down here, and then there's a fourth mirror and actually a whole host of other smaller mirrors that help disperse and distribute that light to all the different sensing equipment on board. Not really going to talk about that, just that primary thing there. So every single mirror itself it's not just a copy. It's not just an 18-segment copy. Every single segment was custom built, custom designed with ever so slight variations, ever so slight differences for its own special unique position in that array. So mirror A1 is just ever so slightly different and unique and had to be manufactured just ever so slightly different than B1, then C1, then D1, all of those. So the position in the array required that those mirrors just be slightly different. So what does all this mean? Strap it all together and let's get some statistics and some data from the astrophotographer's perspective of things that we care about as an astrophotographer. So the focal length, or basically the distance that it takes from light to hit that first primary mirror to hit the sensor of the camera, is 131 meters long. It's over a football field long, but the telescope itself isn't that long. It's because that light path hits those mirrors, bounces back and forth, bounces back and forth, bounces back and forth across all those 4 mirrors, that the actual distance, the focal length from the first mirror strike to that sensor, you count all of those bounces back and forth. So that light path is 134 meters, or 131,400 millimeters. If any avid astrophotographers out there that want to do your own calculations for kind of the James Webb Space Telescope, that's going to be one of your first pieces of information to use on this, is that focal length. So the aperture, mentioned already, is 6.5 meters across. We just go off that primary mirror. And so this equates to a focal ratio of f20.2. So are anybody astrophotographers and or normal photographers out here? Digital photographers, anything else? Familiar with those lenses? So if you have a digital lens, you'll see printed on there an f-stop, an f-ratio, f2.8, f4.7, things like that. This is identical. It's a unitless number that's just a ratio of that focal length over the aperture, and it just kind of gives you the speed of the light gathering power. So like how long would you have to point at an object to gather the same amount of light information from an object? This is quite slow, but that's fine. We got quite a bit of time on this. So one of the resolution things in terms of like how fine of detail can a telescope, can a primary optic of this size gather, we're going to use the Dawes limit on this. And so the Dawes limit, in a sense, is just kind of like how close together in the sky can 2 point sources of light be and have this telescope resolve it as 2 separate sources of light, as opposed to merging it and seeing it's like, I can't make out the detail there. I'm not sure if that's 1 object, 2 objects, 3 objects, 4 objects. I just can't resolve that fine of detail. So the Dawes limit is, with the reduction here, you basically just take 116 divided by the millimeters of the aperture. And so the James Webb Space Telescope has a Dawes limit of 0.0178 arcseconds. If you're already an astrophotographer, that is minuscule. That is fantastic. We'll get an example of this in a moment. And so there's a caveat here. There's very, very heavy nuance to this Dawes limit, using it for the James Webb or any sort of space-based telescope. Because this calculation for the Dawes limit, it assumes it's a point source of light. It assumes 450 nanometers of light wavelength. There's a whole bunch of assumptions built into this, but it's a common metric that people in astrophotography use to know, well, what is the finest level of detail that the telescope itself can capture, and then we can use that Dawes limit to use that and match it to a well-paired sensor to make sure that we are maximizing the fine detail resolution of the images that we're, or of the data that we're capturing. So if you, next slide. So in general, the larger aperture of the telescope, the finer detail it can resolve. So the James Webb, as mentioned, in general, with a decent-sized asterisk here, can resolve as separate 2 distinct point sources of light down to 0.0178 arcseconds. Compare that to a common-size amateur astrophotography ground-based telescope of 120 millimeters or 4.7 inch grand total diameter instead of 6.5 meters, and that can resolve 0.96 arcseconds. Big difference, about a 53 order of magnitude, not order of magnitude, 53 times difference. And surprise, surprise, 120 millimeters, I chose that because that's the telescope that I primarily image with. So the James Webb, just by its very nature of being a big honking telescope, is able to capture much, much finer detail of the same object. If I was to point my telescope with the camera that I have at the exact same objects and zoomed in so you could even compare the images side by side, it wouldn't even be a contest. I would just see basically a blurry mass compared to what the James Webb is seeing. So one of the first images that we're going to return to a couple times tonight was from the initial data download from the James Webb, was the Karina Nebula right here. So actually, Aaron, it might be worth it to put off the lights because we never want to wash out the data representation of James Webb. The top left row. But there we go. Nice Karina Nebula. So, we can actually give a little bit of a side-by-side, not quite apples to apples comparison between the exact same object from even, space-based telescopes, the Hubble versus the James Webb on the exact same object, and scaled side by side. So you can see here that there were, of course, advances in camera technology as well, but in general, just the fineness of the detail. You can see a very, very clear difference as you get into like down here of the Hubble. It's fantastic on its own, but the James Webb, just by its own nature of being a much larger telescope, is able to pick up all this fine variation, smaller detail, all of these different stars and things like that. And I'm actually going to keep the lights off a little bit. So, on to the calibration, collimation, and artifacts.
Let me know when you want me to turn it back on.
Mm-hmm. Yeah, I've got quite a few of these in this section. So first of all, when James Webb was basically deployed and made sure that everything was functioning and communicating and things like that, and basically it unfurled and opened up its mirror array and say, all right, we're going to point it to a star and we're going to take a picture. This is what it returned, was all of these different spiky things in all these different areas. This was to be completely expected. And this is not a star field. This is not a star array. This is a single star. And this is what James Webb returned. And like initially it's like, oh no, we have another Hubble on our hand. We're going to have to go send a rescue mission and just repair all the optics all over again. Oh no. But this was actually exactly expected, because by the nature of the design, it's not a single telescope, really. Because of that segmented design, it is 18 individual telescopes that now we need to shift and organize and just kind of manipulate so that those 18 individual mirror segments align with each other and with the rest of the mirrors and the sensors on board in order to behave like a singular large telescope. So the first, the things that has to happen for that before we can actually start getting the data to get images like the Karina Nebula, we have to do the segment image identification, adjust each segment, then do an image stacking, but really this is aligning each segment. This is not the same as astrophotography image stacking, and ultimately image alignment. And as well, the clean data here is in quotes because this just means like, well, ready to capture actual data that we can use for science and creating these images. It is not the case that we can then, it's already calibrated and pre-processed and things like that. So first up, well, how is that accomplished? Well, on the back side of every single one of those mirror segments is a little hex landing area with some flexures on each side, and those are connected to this baffle here. And on this baffle there are 7 actuators. There are 2 that rest against each of here, and then there's a 7th up here that's connected to a series of struts out at the edge. And so what that allows NASA to do is, for every single one of those mirror segments now, we can move each mirror segment individually by translation, pitch, tip, tilt, rotation, all of those things, so that they can become in alignment for the overall curvature of the array. And then that 7th one, the strut, also can flex and change the curvature of each individual segment to itself to make sure that it is basically a well-curved mirror on its own, as well to follow the complete curvature of the whole thing. So if we go back to this real quick, where it started, we have no idea which segment, that A1, B1, C1, A2, things like that. We don't know which mirror segment actually corresponds to which of these images from the first star. So we have to do segment identification. So from that initial, we just had to go through and say, well, we're going to send a command to wiggle the mirror of A1, and we're just going to see which of those ones wiggled. And so now we know which image corresponds to which mirror segment. And we had to do that for every single mirror segment. So if you are a visual observer or astrophotographer, and say you use a Newtonian reflector type telescope, and you have 2 mirrors to collimate to get in alignment with one another, as well as the focuser, and that can be a painful, arduous process. If you have a Ritchie-Chrétien, I'm sorry, it's even more painful. So we had to do this for 18 segments, both to itself and to each other. So the first step was really just identifying which one was which, and then shifting them with those actuators to make sure that they are in that good hexagonal type arrangement, so that then we can do the next step, which is segment adjustments. Now that we have each one identified, now we can use that 7th actuator and move those struts in and out. And this is essentially like getting that area just smaller and smaller. So now we get the curvature of every single mirror to come to a nice pinpoint sharp focus of that individual star for each segment. But at this point, the James Webb is still just behaving as 18 separate individual telescopes. The next step that we have to do is then do image stacking, or really just align every single one of those 18 segments to a single point, so that all the light gathering power now is into the exact same one. So we have this here that you can see as now that tip, tilt, and curvature to each other. The previous step was making sure that the curvature inside or inherent to each mirror segment was completed. Now we are trying to get the curvature of the entire array in line and all focus at the exact same point. And now we can actually start getting our first star. And so the result of that, this was after our telescope alignment evaluation image. This was one of the first things that was released by the James Webb before it did the actual data dump, since this was still part of just basically turning it on and making sure that it worked. And this is what we got. And I haven't run the full calculations on this, but this is where if you did like the analyze those diffraction spikes, which we'll talk about in just a couple minutes, as well as the detail that is resolvable from this compared to that mathematical perfection limit, this is behaving better than expected. It really is, I can't say with certainty, but one of, if not the best, optical devices that humanity has ever actually manufactured. And as a side note on this, resolution is so great that even on this telescope alignment image, every single one of these other little orangish blobs that you see, it's not a star. Those are each one an entire other galaxy that we're seeing even just within this alignment image of just, let's just turn this on and make sure that all the mirrors are focused by themselves. We know which mirror is which, and that all mirrors are pointed to the same sensor, and we're getting that amount of galaxies already. Wonderful. So the last step is the instrument alignment. So we'll see this animation a couple of times, but now this is more in line with kind of quote-unquote traditional amateur Newtonian reflector collimation. We had to move and shift the entire segmented array and make sure that was in alignment with the secondary mirror that was actually shifted around, and the tertiary, so that the data that we're getting now is actually well focused and falls correctly on all of the sensors. So we're starting there. That was your alignment star, or the image stacking evaluation star. And so now as each of those little things just shifts just a little slightly bit, now we're doing that and making sure that we get good, clean data across all of the instruments at the exact same time, so that you don't have to, shift the telescope around for different instruments. If you're looking at the thing, all instruments are on it. And so that's what we get here. That right there was basically the alignment evaluation star. And then once everything was all set up, then in that same area, or at least the same region of the sky at least, now everything is all in line for all the instruments. We have our NearCam, our near-infrared camera. That's what we're going to be focusing on tonight. Our MIRI, mid-infrared imager. NearSpec, near-infrared spectroscopy, spectrometer, near-infrared slitless spectrometer, which is really cool, and fine guidance sensor, which for any astrophotographer out there is basically the same thing as the autoguider. It's really just making sure that for those long exposures that the James Webb is steady, stable, and can maintain its pointing accuracy for effectively however long it wants. So I want to go back to this telescope alignment evaluation image. So for astrophotographers that do use any sort of telescope design that has a suspended secondary or tertiary optical element that has like spire vanes or things like that, we get these diffraction spikes. You might think, well, you know, first look at this. Well, we see all these galaxies. That's cool. It doesn't have spikes. How come this star has these giant spikes out of it? Is something wrong? Do we actually need to go out and service this or anything? And no, this is another thing that is completely expected, as well as just an artifact of the optical design itself. And the source of that, the diffraction spikes come from, we saw back how that secondary mirror is on kind of 3 spokes to hold it and also be able to shift it around for that alignment. So those are those 3 spokes right there and the secondary mirror. So on any mirror device, on any optical device really, if you were to cover part of your primary optic with a pattern like that, and you get a strong point source of light, you're going to get a diffraction pattern, or basically a scattering of the light from those things in front of your mirror in that pattern. The other parts of it, this general 6-pointed star, that is just the natural pattern that arises from a hexagon style mirror or hexagon style scope. So as amateurs, we are most familiar with you know, perfectly round, or not perfectly, but just circles. Circle as your mirror, circle as your lens. And so we wouldn't get that sort of diffraction spike, and the only diffraction spikes that you get would be from the spider vanes or the holders of the secondary. But if you overlay those on top of each other, then that is the diffraction pattern that you get. You get a combination across some of the primaries from the secondary holder, and then you get these smaller spikes that are leftover artifacts from the secondary holders. So anything like that, it's by the optical design. Okay, Ursula. So field of view. What are we looking at with NearCam, right? So the optical design with that focal length, the diameter or the aperture, combined with the size of the sensor, and so we will just be talking about NearCam specifically as 10 total sensors. So that combined with the fact that it's 18 micron pixel pitch determines the amount of sky captured by a single image or a single frame. So the NearCam, it actually had those 2 squares as we saw a couple slides back, and so it looks at 2 distinct 2.2 arc minutes of sky at a time, which is quite small. So one thing that I personally at least obsess about in my own amateur photography is the sampling rate, or basically how much sky falls on each pixel of my camera. So we can, that basically gives you the effective resolution of the data that you're going to capture. So we have the Dawes limit of the optic itself. Cool. But we combine that with the size of the pixels on our camera to determine how fine of detail we can actually pick up. So the NearCam has 2 different kinds of sensors that it uses. And so the sampling rate of the short wavelength is 0.031 arc seconds of sky per pixel, which is tiny. Yeah. The long wavelength is double that. The pixel pitch is pretty much twice as large. So what that looks like here, the NearCam is set up this way, that each of those squares, each of those 2.2 arc minute patches of the sky that's looking at, got 4 sensors for the short wavelength, and then a single sensor for the longer wavelength. And we have a second one over there as well. So 8 sensors for short wavelength, 2 sensors for large wavelength, but they're basically looking at the same thing, and there's just some optics and light path splitting that's happening on board. But that's how it's combined to get, again, back to the image of the Carina Nebula. So now we can understand a little bit more about all of the nice fine detail, all this ghosty stuff, and why all of these bright stars have the diffraction pattern that they do. So, okay, want to use this Carina Nebula as well because I've got a short video here. Well, okay, this Carina Nebula is, it's just stunning. It's one of the first pictures that we had access to. And the Carina Nebula is on its own a pretty large nebula. It's generally a southern hemisphere type object, so Keith might have an opportunity to view it. But, okay, well, I hear that. I kind of understand it, but I can't visualize where in the night sky this actually is. What am I looking at here? Let's take a look. So this was used by Stellarium. So the horizon, and zooming in, that is the Carina Nebula. That's basically a ground-based telescope in Namibia. So we'll zoom in on just a part of that. And so now we've got an ESO observatory down in Chile. We'll zoom in even more, and now we can start to see that defining feature. Now we see that wave. That's how much we're zooming in. That's how little of the sky we're looking at. That was the image taken by Hubble.
Let's do that again.
It's not done. No, we're going in. So now zooming in even closer to Hubble, but now we see that smooth transition of all that extra fine detail that is caught up. So that size, that 100% zoom from James Webb. So we transition from the Hubble viewpoint to the data from James Webb to see that additional detail that is captured just by nature of it being such a larger telescope. The background against this is the Hubble, and this is the overlay of the James Webb detail of that. Let's put that back in context and zoom back out. And even that was still a mosaic from James Webb. So for every image, that's what we're looking at. That's that focal length ability of the James Webb. That's the amount of detail that it can get while still zooming into that small amount of the sky.
That's really cool.
Let's get a few more examples. There we go. So that's still pretty abstract. It's like, well, the Carina Nebula, I kind of saw it on the horizon and things like that, but it's still kind of tough to, you know, how big is it in comparison to something that you might be more familiar with? So let's take a look at the moon. So I put in the information and the data on my own up here for the NearCam and James Webb Space Telescope in Stellarium. It's a free program you can get. And forgive me because I just kind of winged it, and so my sampling rate is off by 0.001 arcseconds per pixel from actual. Forgive me for that. But from here, we have the horizon, and we've got the moon. So let's zoom in a little bit more. We've got the moon, a little bit bigger. Can anybody from here or there see where the field of view square is for the James Webb? Not quite yet. What about now? Getting there, right? More in. So the James Webb, the NearCam, that is a square that is 2.2 arc minutes by 2.2 arc minutes. And so each of those 2 NearCam arrays is looking at an area of the sky that big for context and getting that level of detail out of it. That's the stunning bit. Well, all of it's stunning, but that is really what is so amazing of it. Ground-based telescopes could make it so that we are looking at the same small patch of sky, but the ability to get that fine detail and that data is really what makes it stand apart. One more example. So I can't see hands, but I'm still going to ask the question anyway. Is everybody here familiar with M16 or the Eagle Nebula or the Pillars of Creation? Yeah. Let's take a look at that. So from here on the horizon, we have M16 right there. So we have the nice Eagle Nebula, and the same sort of thing here, that up over here we have the red square superimposed on this for the NearCam and James Webb Telescope. Can anybody see the red square yet? No, that's fine. Zoom in and enhance. Got more here. So the overlay is a little bit tough here, but the imaging that we're seeing from James Webb is this square right here in the heart of M16, the heart of the Eagle Nebula. And we see right there, those are the beginnings of the characteristic pillars of creation. So that is the field of view. Well, cool. That's probably about what I could get on mine, on my astrophotography rig. James Webb got that.
Wow.
Yeah. Cool. Okay. So that is what we're looking at in the sky when we get the images from James Webb.
Is that a mosaic?
I would have to double check. So one of the things that I didn't quite have time to dig deeply into myself, but one of the many, many wonderful things about James Webb as well as Hubble is that it's yours. You know, your tax dollars and global agencies paid for this, which means all of the raw data is public access. So I didn't download this. I downloaded a couple of the raw data files from the Karina Nebula, and it didn't finish because, surprise, surprise, the raw data files from James Webb is large. But ultimately, for any astrophotography processing nuts out there, there's a completely free portal where you can get all of the calibrated, aligned, stacked, and pre-processed data from James Webb and do your own image processing on it because it's yours.
We got some wow comments.
Mm-hmm. Okay. Well, okay, that's in the sky. That's what we're looking at. Like, no. But what the image? But what are we looking at? Are those the real colors, right? So we look at this. Is that the actual object? Is that really there, or is this just, you know, what, quote unquote? I'll be honest here. My most hated phrase in all of astrophotography is false color. There's no such thing. So it's like, well, isn't this just false color? Let's talk about that. So I've been trying to be very careful throughout this presentation that all of astrophotography, amateur and James Webb Space Telescope, is ultimately aimed at capturing data on our camera sensors. What we get is highly accurate information about the light emitted or the light captured from the object. Once we have that data, once we have the very real light-based information from the thing, we can present that however we want. Ultimately, for like the science, like all of the images that we see of like the Karina Nebula and the Pillars of Creation and things like that, science can be done from those images itself, but that's not really the data that's going under heavy analysis, especially on the spectroscopic side of the sensors. So the data, the information that we get from the objects themselves, it can be as reductive as just well values on pixels in an array. Pixel, you know, X position, Y position, 14,000, blah, 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 had a value of this. That's our data. But that's the same for all astrophotography. So we can use then that data and do whatever we want with it. We can present it as just an Excel sheet of numbers, or we can present it as an image. So ultimately here, the mirrors gather and focus the incoming information that's real, that's from the object, from the stars, from the nebula, from whatever it's looking at. And filters that are placed over the sensor only allow specific information through at a time. Then this light that's going through those filters combined with the sensor sensitivity captures that information, and then that information is assigned to color channels and processed to basically what we are doing in all of astrophotography is presenting a visual representation of raw data that a digital sensor captured. Well, let's talk a little more about that still. So the NearCam filters themselves, this is a full set, or the full set of filters that can be put in place over those sensors of the NearCam. And it shows here that it basically has a different passes of wavelengths, so only certain wavelengths of light are able to be captured by the camera, captured by the sensor at any given time. So the Karina Nebula image was captured using F187, so data was captured from the object in 1.8 micron of light wavelength, 335M, so up over here, got some green, yellowish data information from the target. 090W, so nice purple, 200, nice blue, and 444, a lot of red. So really, what we're doing here is we are capturing a whole host of different types of light information from the object using these filters. And then we assign that information to color channels in order to make an image so that we can visually represent the data captured that we allow through using these filters. And by doing that, we can get this sort of visual representation of the information actually recovered by James Webb. So let's get a little bit of a showcase of one of my own data sets. Giant asterisks here. This is an incomplete final image. This is not my final result. But just to give an example here, because all of the sensors on James Webb and many astrophotography amateur sensors are monochromatic. They just have raw voltage values within each individual pixel. That's what we're actually gathering. So for one of my images, this is what the camera actually gathered as data using a red filter. This data set has been pre-processed, it's been stacked, and it's been through mirror denoise for any astrophotographer out there. That's it. That's what I got. That's the data. Cool. Well, I want to visually represent what the camera actually captured a little bit differently. I want to make it more aesthetically pleasing. So I can stretch it, and now we kind of see all sorts of information that was still present in those images, but it becomes more apparent to our eye. So this is how the data can be represented. So that was with a red filter, kind of like that F444W from NearCam. That was with that a similar sort of filter placed on my own camera with my own telescope. Now we can do the same thing for data captured using green and blue filters, but not green, that's not allowed. And then we get different data sets that correspond to each of those types of information coming from the object, and then we can combine that and stretch it, and we get a color image. And again, A peers take note. Literally, I just did a mirror denoise stack channel combination and stretch. Not my final work. But this is essentially what is happening with the James Webb or any astrophotography. So again, really all these images, are these the real objects? Is that what they really look like? Isn't that just false color? Well, we captured data. And the information that we captured from this data, we chose to represent visually. And we can do that in a whole host of different ways. But ultimately, the light comes from the object, and that light is very real. You know, different filters on different objects would give you different information. Maybe not at all. Maybe the object isn't emitting that sort of light that we can assign to the different color channels in our representation. But ultimately, that is what we're doing. So with that, then, we get all of this data, we do everything, and we can get these stunning representations that we've seen of all of this glorious detail and types of information that we are getting from this based on the size of James Webb combined with the wavelength sensitivity of the sensors that we have on board to see things that we've never seen before. A lot of the initial objects that the James Webb has looked at had been things that we have already gotten data about from Hubble. Once we can do a side-by-side comparison and just say, oh my God, this is that much better. but also because, especially with MIRI, the mid-infrared, the type of information that we are getting from these objects using James Webb is information that we have never had access to before on these objects. We are truly, truly getting a brand new look at the entire cosmos in ways that we haven't seen based on the data that we can gather from this. So we are truly just at the start of the era of the James Webb Telescope. Thank you.
Yeah. All right, everybody ready for class?
Tell your right.
Wow, that was a journey. I wish I brought my popcorn and and everything else there. Okay, but we'll start brainstorming some questions for Sabrina. I think one came in.
Ultimately, just wanted to say the main takeaway I wish to leave you with on this is there's no such thing as false color. It is all just visual representation of data. That is all astrophotography.
Yeah, that's great. Thank you so much, Sabrina. That was really cool. Paul was asking towards the end of your presentation. Paul, do you wanna unmute yourself and ask your question that you had for Sabrina?
Yeah, fantastic presentation. Thank you for for putting it out for us. I just didn't realise that some of these pictures is just so good. But I was wondering about dithering and if it's done with these types of telescopes, and if it is done, how's it achieved? Because clearly you're not going to shape things. So do you have any ideas on that?
I am not 100% sure on that. I have not been able to find information on a deep dive of precisely like the data acquisition techniques. So the question is, does the James Webb do dithering in its data acquisition? So in astrophotography, dithering is a technique that when you stack multiple images of the same target, it allows you to effectively increase your signal-to-noise ratio. So sensors, camera sensors, digital camera sensors have noise inherent to them from a whole host of different reasons. That'll be a different talk for a different time. But one kind of source of that noise is inherent to the camera sensor itself, and it's similar or the same to that sensor, image after image after image after image. This causes an issue because if you were to then take multiple images, and that noise is in the exact same location every single time, and then you combine all those images, you're going to have huge amounts of noise in those locations. So what dithering is that I want to take an image of the Karina Nebula. I take an image and there's noise inherent due to the camera sensor. Well, on the next frame that I'm going to use to get more information from the object, I'm going to shift my frame like 5 pixels, just a little bit different, so that the noise pattern on the sensor in relation to the stars, in relation to the signal that we care about, is different. And so in processing software where we get those collections of data and we combine it to improve that signal-to-noise ratio, the way that we do that, called actual image stacking, the noise that is inherent is drastically reduced because we can identify it because it's actually different frame to frame, pixel to pixel. So with that aside, I would overwhelmingly expect James Webb to do dithering for that reason, because it does also help with scientific investigations, because especially if you are trying to gather data on very low signal things, you need to make sure you have as much of a signal-to-noise ratio as possible. So I would expect it, but I cannot say from authority that James Webb is actually doing dithering. A very long-winded explanation of that.
Thanks, Sabrina. I'll go back and forth between in-person here too. Do we have an in-person question here? All right. Can you share your name?
Yeah, my name is Ruben.
Ruben.
So the spikes that we were talking about
Yeah. So the question is the artifacts that we see, the diffraction pattern that we see from the secondary baffles, as well as just the hexagonal design. How come we only see those on bright point objects or stars instead of like also seeing that on galaxies and everything else as well? So for that as well, one, it is a very good litmus test for kind of what you're looking at that we can see in the data as well, is that if it has those diffraction spikes, it is a star within our own galaxy, or it's part of a nebula within our own galaxy, some sort of diffuse type thing. If it doesn't have that, it's a galaxy. But ultimately, it is the result of the intensity as well as the point source nature of stars. So stars are so far away that even with the power of the James Webb Telescope, the sensor size, the focal length, and things like that, the photographically, stars are effectively still at an infinite distance away. So in a perfect world, a star would just hit a single pixel. But because it's coming in, part of that light is going to be, hitting those baffles and be, dispersed and spread out. But it has to have a strong enough light source. There has to be enough photons hitting things during an exposure so that some of them get reflected out, some of them get dispersed, some of them get dispersed around by those baffles and captured in that way. And that's all. Does that make sense? Okay.
In Vasuki asks, which star was used for the alignment, if you know, and how did they choose it?
I don't know.
Not sure. Well, we'll try to get back to you on that. How about Chen?
I think it was in Ursa Major, but that's as specific as I can get.
Yeah. If anybody on the Zoom world is on the interwebs, feel free to look that up and post that answer in the chat. Chen asks, what mechanism does JWST use to track the stars for long exposure shots?
Yeah, so that is part of that fourth mirror or the fine alignment camera. So it uses it's I don't know in terms of like thrusters or gyroscopes or rotational things or things like that. That sort of mechanical control. I don't know, but it does have on board what is basically literally exactly like an astrophotography auto guider. So with those point sources of light, since stars are, we can identify them as stars, and we know the sort of diffraction that they would have, or ultimately what's called the point spread function of those stars due to optical stuff. That would be a more advanced talk as well. But ultimately, we know that with a point spread function based on the optics, and we don't even have to worry about seeing conditions because it's in space, that star should be on a singular pixel. And so there's a separate set of cameras that basically are looking at that star field and picks a star, or picks basically a series of stars and then does some other calculations for the more advanced stuff. But effectively, it looks at a star, says, well, look, in a perfect world, that star better not move from this pixel no matter how long I point at it. But then if there is a little bit of drift, it says, oh, no. I know this data. This star that I'm tracking is now on a different pixel. Ooh, that's going to make for a blurry image. So we better send a correction and make sure that as I'm tracking that star is going to maintain exactly on that pixel. And that way we know that the rest of the data incoming from the telescope and being captured by all the other sensors are also perfectly aligned and maintain that steadiness for the long exposures.
Oh, and just a quick update. John McLaren, former president, alignment star, the star. Alignment star was HD 84406, of course.
Clearly.
Used because medium brightness with few other stars in the field of view. So yeah, thanks, John.
Thank you.
In-person question? Maybe like five months in a minute. Go ahead.
Yeah, so this is following up on the last in-person question. If the spike artifacts are so predictable, why don't they get corrected out?
Ooh. two answers to that. Three answers to that. One is for many folks, those spikes they look pretty. So let's keep them. Really, the correction for that, there's nothing on board that would be able to correct for that in terms of like a optical mechanical type pathway to correct for that. They could be corrected in post-processing, basically digitally removed. But we spent billions on this, 15, 17 years on this. And so even those diffraction spikes can give us information and data about the intensity of the stars that cause those things. And even if those spikes are optical aberrations, it's still data. And data is data. And every single pixel well count captured on anything by James Webb is precious. And we don't want to just delete that out.
I'll go online real quick and then back over here. Sabrina, maybe if you can MC the questions here. I don't have a good angle here.
Sure.
Oh, this is a fun one. Kind of less on the photography side, but since we don't have a space shuttle, how do they plan on future repair of the telescope?
They don't. This is the thing. This was a one-shot. We had to get it right. There is no repairing this. There is no servicing. There's no sending out upgrades to it. It is parked way, way out at a generally gravitationally neutral point called Lagrangian point 2. It is so far out there that I can't say never. Could do it with robotic space arms, this sort of a thing, but not a manned crew out there. It's just way too far. So that's why there were so many delays, as well as the launch was just so, just adrenaline fueled, and why like every single bit of information just like the sun shield was extended, yeah! Because if like one critical system, one critical thing failed on this, the whole thing fails, and we're not going to be able to save it. So no plans to service, no plans to do it once it has reached the end of its service life, not necessarily mission life, because NASA has a fantastic track record of lifetime of missions far exceeding the planned mission time, and hopefully that happens here as well. But once it's done, basically once it is incapable of sending us data back, James Webb is done.
A couple more in here.
On the correction of the people, is that done automatically, or are we sending a signal to correct?
Oh, okay, so like mirror correction or things like that. We are sending.
Well, can you repeat?
Oh yeah. So the question is, so like mirror alignment, or like the flexure stuff, sending those actuators and like all of those things to get it ready. I don't know how long of a delay that is, but we are sending commands. So that's why it's such a long process when it's like, we got the data, we got that initial star field array, and I believe it took just over 3 months in order to start getting actual data from the James Webb, because that's how long it took to send a command, wiggle the mirror, take a picture, send it back, compare, oh, that's A1. Send a command for this other mirror, take a picture, send it back, compare. Oh, now it's up 18 times. Then do that again and again and again and again to fine tune and get them in, all the stuff that we saw. So, yeah, took a while.
Yeah, thanks for that question. Aaron Garland asked on Zoom. This is a fun one. Will future astrophotography cameras and telescopes emulate the design and function of the JWST? What does it inspire?
Ooh, the sensors. Absolutely. There are a couple of sensors that are available to the general public that could be similar-ish in behavior to this in terms of being more sensitive, more towards the infrared spectrum. That is where astrophotography gets expensive. But in terms of like pixel size and like array size and things like that, they're actually not that big. But the sensitivity, the dark current, the other control and things like that, yes. The optical design, the arrays for astrophotography would be a high challenge. I don't know of anything on the horizon or anything that will be available to the amateur that would be similar to this. In terms of like the that Korsch style triple anastigmatic reflector thing. This is the first I've ever heard about it. So I don't know of anything of that particular optical design that will be available to the amateur. So the one...
And the question was how big the data files were.
So the one data file zipped from a single filter from a single square of the NearCam in the zip was 880 megabytes. And then I foolishly started to try. It's like, well, I want all 5 filters, and then I went to bed. So yeah, and if anybody's interested, if you send out the Zoom link, I can append on the database so that you can also search through and you can download the raw data, the calibrated data, the stacked data, the unmosaiced. It's all yours. And I found a portal to that where you can even specify it down by mission type, by sensor type, by filter, and by object. So you can just say, it's like, I want just these data sets of this filter from NearCam on Pillars of Creation. Boom, there are your 6 files.
Good to know.
So when you're talking about images, some people talk about Hubble images using the palette.
Yeah.
And we got the James Webb.
Ooh. I believe last month's speaker or speakers a couple times back was actually discussing how the color palettes were chosen for James Webb. I did not see that. Short answer is I don't know. So the Hubble palette in astrophotography is a very specific set of filters placed over those sensors. Most commonly filters that only allow through hydrogen alpha wavelength light, oxygen 3 wavelength light, and sulfur 2 wavelength light. And so the Hubble palette, or the SHO palette, SHO, assigns red to sulfur, green to hydrogen, and blue to oxygen, SHO-RGB. That's the mapping that results in the colors that you see from the Hubble. 3 filters, 3 color channels. Cool. Well, even the Karina Nebula used 5 filters. Well, how do we assign data from 5 filters to RGB, to 3 color channels? It's a blending of it. I don't know how they do it. Can't remember her name, but there's a principal image processor for James Webb data, and my God, are we all jealous of her job. But it's a blend, but it is basically at this point generally prescribed blend that, this filter would be assigned to the red channel by 20%. This channel would be assigned to the red channel by 80%. Some mixture on that based on data sets, filter sets. There's so many more filters, so many more data sets available to use from James Webb that I am punting the question by saying I don't know. That'll get you there.
Mike, this might be the last question for online, and then maybe we can finish off with a question here. Mike K is asked, is JWST taking darks, flats, and flat darks for post-processing just like astrophotographers do? Something that's a little...
Right. So that is standard astrophotography calibration, and that is what is used ultimately for quote-unquote clean data by amateur astrophotographers. So you get a raw data set. You actually download an image from the camera. It's going to be noisy. There's going to be curvature aberrations and things like that, a whole host of stuff. Well, first and foremost, I'm not 100% on many of these things. However, flats aren't needed. By the nature of the optical design that Korsch reflecting anastigmatic design, because the curvature of the mirrors interacting with one another are there, you get a flat field across the sensors. Flats aren't needed. Flats aren't needed. Flat darks aren't needed. The darks, I don't know. I would expect there to be some sort of dark library, or at least a couple of a dark library of super, super, super long exposures. These are, I believe, still CCD sensors, not CMOS sensors. It's getting deep into the weeds of astrophotography here. But ultimately, only on CCD type sensors are long exposure dark calibration frames linearly scalable to any length underneath of it. So we have a dark on the sensor that we could have captured on Earth as long as we got to the similar temperatures and things like that. And on Earth, we took a dark frame, which is basically just covering the sensor, not letting it gather any light, and we got that for 4 hours. We could effectively use that type of frame to calibrate, clean the image, clean the data, effectively get better signal-to-noise ratio at the end of the day for any image that we get from James Webb from 1 hour, 2 hour, 3 hour, anything up through that 4 hour dark, whatever we got. I would expect that, yes. And similarly, you could get that bias frames as well, since you would need that for scaling darks on Earth as well. But ultimately, once it's up there, as long as we have all that information on Earth, there's no reason to get calibration data from James Webb after launch where it's at.
More question or? Yeah.
Oh, one more.
Final
Last
question.
one.
Do you know what the typical exposure is, like, for the nebula? Any idea?
That would be information. I will continue the download at a later time, and I'll see if they have any sort of header information for integration time on either individual frames or total integration time on mosaics and things like that. I'm sure it's different for different objects, but I don't know what it is.
Awesome. Well, we're going to get a little close here, Zoom World. One more time, let's give it up for Sabrina. Yeah, let's give it up. Right, that was fantastic. Yeah, I just want to say, thank you again for everybody coming here today. If y'all want to hang out and say hi to Sabrina or myself, I'm Aaron. I'm on the board, and Sabrina has blew our minds today. That's for sure. I need to just get that clip of that zoom in thing and just Chromecast that thing at home. So, but yeah. And once again, Saturday, March 18th. If y'all are in town, if you don't have plans, we would love to see you at our banquet. We had a lot of fun last year, like so much fun last year, and meet a lot of new people, and it's just a great community to be a part of. So if you can make it Saturday, and just keep your eyes peeled on the website, and consider coming out. I would love to see you. It's going to be a really fun time, and I would love to capture some of the energy we got here today and bring it out there. It's a really cool community to, especially coming out of the pandemic, just seeing new faces and getting people involved again. So we'd love to see you there. And with that, I'll close it off. Thank you for all the great comments. We got a lot of great comments coming in here on Zoom. So very nice job, great presentation. Thank you, amazing so much for, thank you for the amazing presentation. Excellent, nice presentation. So getting lots of love, Sabrina. And and so thanks everyone for coming again. Thank you, Zoom World. And with that, we'll say we wish you clear skies and peace. Yeah.